Okay, hey y'all, good morning. I hope I'm audible to all, right? Can I have a confirmation, guys? Okay, thank you. So, good morning, all. This is Dave on this end. Hope you all are doing great and fine. So, well, guys, for the starters, let me introduce myself. My name is Dave. I work with the Department of Machine Learning, Artificial Intelligence. And for the starters, let's talk about the agenda. So, as written in front of you all, generative AI is going to be the agenda for the discussion of the whole session. Okay. So we are going to talk about various aspects of what this all generative AI stuff and all that is. So without further delay, good morning everybody. This is Dave. Good morning Kishore, Rajaram, Hemant, Shriram, Pooja, Yash, Ved. And as I can see over here, there are few people I believe I might have met earlier. So is there any case we have met earlier, guys? Anyone? Like I can recognize few names from my maybe some of the last classes of ML. I'm not very sure. Good morning, Bhartish. Sorry, Bhagirath. Okay, anyone over here who knows me already, who has already been in my session before? Okay, Pooja is saying no. What about others? We met in ML class. Yeah, Shashank, I remember you. I believe we met in statistics and probability class, if I'm not wrong. Nope. Okay, chalo. So guys, there are just two rules in my class. Okay, as such, the first rule is whenever we are discussing, let's have a full focus. Second thing is there's openness in the class. Okay, so if you guys want to ask something, if you guys want to discuss something, feel free to put your queries in the chat box. Either you can just simply raise your hand and you can have the mic access. Okay, so both the things are actually okay by me. So whatsoever is comfortable by your end, you can just let me know and we'll cover up with like that way. Okay, sure. So I'm still seeing that people are still joining. So what do you say, guys? Shall we wait for 2-3 minutes and then we kick off, or should we kick off right now? Everybody, let me know. Let's start. Uh, let's wait for like 2 more minutes. Okay, Ganesh. Yeah, let's wait for like 2 more minutes, and then we'll start. It's like 7:03. So let the people join by 7:05, and then we'll start, guys. Okay. In meanwhile, let me discuss with you all what. Yes, wait, because people will join and ask to repeat. And that's completely fine. Yeah, that's completely fine. Okay, chalo. So generally, what's the difference between AI and generative AI? I'll talk about it, Shriram. Okay, I'll talk about each and every bits and pieces about what exactly are the differences, what are the use cases where AI is used, what are the different zones of AI and all that. Everything we'll talk today. Okay. Okay, so in meanwhile, guys, how let me ask you all because I generally ask this thing in all of my sessions. Okay, how's the Josh, everybody? Because that's the first thing that I would like to know from everyone. How's the Josh? Because if you guys are not high on Josh, the class will not be as peculiar as it has to be. Okay, only three people are saying, "Hey, they we are high on Josh," but right? Sure. Let me talk. Let me start talking. I think it's like 1 more minute to wait. Okay, and meanwhile, you guys can tell me, are you guys all familiar with the neural networks and all that part, everybody? I believe everyone is aware about those all things. Okay, sure. So in meanwhile, let me quickly share the agenda and quickly share the how the flow is going to work up. Okay, like how exactly we are going to take this session forward. So guys, today I'll be talking bits and pieces. Mostly, if I talk about, let me open my notepad and let me see what we are going to study. So firstly, today we are going to talk about generative AI. We are also going to talk about history of generative AI. Then we'll talk about what were the use cases, like why exactly this thing came into play. Okay. And then we'll talk about some of the core concepts and the uses. And then we are going to talk about something that will be, you can say, the first stepping stone in your journey of generative AI. That is long short term memory. How many of you have read about it, or how many of you have heard about it? Long short term memory. Anyone? Okay, I believe heard, right? Most of the people have heard about it. Chalo. So that won't be a issue then. I have heard it in all the AI classes. Okay. Anyone who has implemented or anyone who knows about it, who have read about it, maybe anywhere somewhere. Okay, Praveen has read about it. Okay, fine. Okay, no issues because there are only few people who might have read about it. Not translated here. Everybody's stock prediction. Ah, yes, exactly. That's correct. So, guys, today we'll have the discussion on LSTM. Tomorrow, I'm going to talk about the architecture of a LSTM, and day after tomorrow, we are going to talk about a case study that I will be preparing. Maybe most probably, I think on the stock data or something, so that everyone could be on the same page. Firstly, we'll start with the smallest steps, then we'll increase our size of steps. Okay. So one by one, we'll talk about each and everything. Okay. So is this completely fine by everyone? I believe the agenda is superbly clear what exactly we have to do. Anybody having any doubts with the agenda? Chalo, what about GANs? We'll discuss here. Okay, we'll discuss one by one everything. Okay, no need to worry about. Chalo. So let's start it with a very basic understanding. Okay, everyone. So guys, if I talk about AI, okay, so what exactly this AI is, everybody? Okay, so in a very nutshell, it's a very big circle. Can I say? This basically this is AI, right? And I believe you guys might have also read about this thing called as ML, right? Machine learning, correct? So this is what is machine learning is. Okay. And then you came across this particular terminology called as deep learning. Oh, quite cracky, right? Then there was a terminology called as deep learning. So basically, guys, if I talk about so one by one, you were deep diving into a shell, right? And then as of today, we are discussing something called as generative AI. Okay, here now. So guys, if you are talking about so generative AI is actually a subset to AI. I would say okay, it's a smaller part to what exactly AI is. So AI is a very broad field. Okay, it's not like it's very small or it's very comprehensive. It's a very broad field. There are a lot of things inside AI that even as of today, the people are researching about it a lot. That okay, how exactly this and that and all that thing is going to work. Now, coming with what exactly is the surreal agenda. So I'm going to talk about what exactly this generative AI stuff is. So what do you think, guys? How old this generative AI could be? Like, what exactly could be the like you can say the initial year when this generative AI was started? Anyone? Just take a guess. I heard too long. Okay, Hemant. Anyone else? Uh, 2000. Okay, 2018. Okay, 80s. Okay, 1930s maybe around 2015. I don't think it's too old. Okay. Guys, let me talk about. Okay, generative AI has a fairly short history. Okay, with technology, it was introduced around the 1960s exactly. Okay, this technology was introduced around 1960, and actually not in 1960, to be very precise. It was introduced back in 1940s actually. The early papers or the early research came in around 1940. The first implementation, DN. No, dear. It's just I'm talking starting about with the AI part. Okay, the generative AI. Okay. So the first paper actually it is not about the implementation, but the first paper, the research is. So the research upon this particular topic started in the early phase of 1940s, and in the 1960 we gotta see the first use case of what exactly we call as generative AI was. So that was a chatbot actually. Okay, it was a form of artificial intelligence that can work with different types of user inputs. Okay, so however, like till 2014, okay, we didn't knew a lot about generative AI, and I believe everyone will agree on the same, right? That yeah, Dev, I think till 2014 this thing was not actually in existence actually, right? We knew about a lot of stuffs and machine learning, we knew about a lot of stuffs and deep learning, but generative AI was not in the game. Okay, so generative AI is based upon this machine learning and deep learning machine learning algorithms. Okay, deep learning algorithms that you might have studied. So the first machine learning algorithm was developed by a person called as Arthur Samuel. Okay, if you guys might want to learn about it, you guys can just search it on the internet. So the first machine learning my algorithm, are defects also a part of Gen AI? Yeah, Pravan. Defects are also a part of Gen AI. Okay. So the first machine learning algorithm was developed by a person called as Arthur Samuel, as I was talking, and it was developed in 1952. Okay. So have you guys heard about checkers, everyone? Or maybe chess, right? So this particular algorithm that was developed, it was for a game called as checkers. Okay, it's similar to what you play in chess. And he was the also the person who came up with this phrase called as machine learning. Okay, so this particular terminology was given by a person called as Arthur Samuel in 1952 actually. Now, I think when you guys were talking, when you guys were in the class of your neural networks, right? So if I talk about a bit about neural networks, guys, the first neural networks actually that was capable of being trained, that you very, I think very strongly you call it as perceptron, right? I believe a single neural network, right? It's called as perceptron, guys, correct? So this particular first concept of this perceptron was developed in 1957 actually. Okay, in a university called as Cornell University by a psychologist called as Frank Robspalt. Okay, so the perceptron design was very similar to what you see the model neural network is, but only had one layer. Okay, only had one layer containing the adjustable threshold, weights, your input and outputs, right? Now, guys, can you think of it like why exactly that old one, okay, the one that we are talking about, the 1954 7 creation, why it got failed ultimately? Anyone who can think about it? Think about it. It's very interesting if you guys are, see, if you guys are aware about this history, right? So you'll be very easily able to learn about what exactly is the current implementation. One layer, okay. Anyone who would like to have mic access and would like to answer the same question? What kind of tool and sources they used to develop at the initial? It was mere mathematics, Shriram. Okay, computation space, data. What was the question? Question was there that the perceptron model that was generated in the early 1957. Okay, and if we compare it with the modern neural networks, right? So what could have been a difference actually? Accuracy. Guys, I think the main reason was that the system was too time consuming. Obviously, because someone has given an answer before that was just having one layer. Okay, one layer. That's it. One layer is very, 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 very small if you take talking in terms of today's data. It will take eternity to get trained. Don't you think, everyone? Is my understanding correct? Obviously, computation problem, right? So now let me talk a bit about, because now we are see guys, I'm talking something like this. Okay, let me write over here. Current Gen AI is able to create new patterns after understanding a correct pattern, but the AI only understand patterns exactly here. So what I'm trying to say is, guys, over here in 1950s, okay, we already had an idea of what exactly neural networks looks like. Okay, though we were not able to make such very, very, very complex neural networks. Okay, it was like just one layer, or maybe at max if someone can push, because if you remember in 1950s we didn't had that capabilities of computation, right? We didn't had that GPUs and CPUs that we have today, right? And maybe if I talk 10 years after today, okay, then might be the students who would be learning, or maybe the professors who would be teaching at that time, they would say that okay, in 2024 we had like a system of 128 neural networks, and I think if we compare it with today, what will the difference? Then again, the same answer will be there, the computation issues, right? Now let's push ourselves to 1960s actually. Your voice is low. I believe, guys, my voice is audible. Is my voice audible to everyone? Can I have a confirmation? Chalo. Generally, guys, I speak a bit low, so yeah, I'll recommend you all to please increase your volume if in case it's coming. Okay. Chalo. Now let's talk a bit more about 1970. It's that the highest. Okay. Generally, guys, I speak a bit low, so if in case if there's a lot of issue on your end, you can let me know. Okay, I'll try to increase up my volume, or maybe try to set up my mic adjustment. Okay. Yeah, I'm using headphones, dear. So, Rupali, you have raised your hand. Any such concerns, dear? Sure, no issues. Okay. Now let's push towards the topic of 1970. Okay, can you show an example of how initially this AI started? Okay, dear, I'll tell you. Okay, let me talk about an example. So the very first historical example of generative AI was ELISA. Okay, let me show you what exactly was ELISA. So this is ELISA actually. Okay, ELISA was the most early natural processing computer. Okay, developed between 1967 to 1964 to 67 by MIT. Okay, by Joseph Wozniak. So basically, guys, what I wanted to tell you is the very first neural network. Okay, it was this ELISA, and it could be also considered as an early version of chatbot actually. Okay, it was a talking computer that would respond to human using your natural language, and responses were designed to sound like empathic. Okay, like if you're asking something, hey Lisa, can you tell me this thing? So instead of like today how exactly Google talks, it was mostly like empathic language, trying to express empathy kind of. Okay, then in the early 1960 to 70, this research on this computer vision and this basic recognition pattern started. We started looking into facial recognition, and there were a lot of people who worked upon it. So if I mention some names, there were Leon D, there were Harmon, there was AJ Goldston. So these were the people who developed around 21 specific markers, including like characteristics like thickness of lips, color of hair, how exactly your eye texture is there, then how exactly your ear texture is there. So these were some kind of human face identification techniques that were developed in that early phase. Like remember, like try to imagine, guys, it's like 1952 or maybe like 1972, when there's a specific group of people without having that much computation, they are working with this all things. Okay. Then I believe you might have heard about this thing called as back propagation also. Have you guys heard about back propagation? Anyone? I believe most of you would have also worked upon it. Okay. So in 1970s, this back propagation began. Okay. It was introduced by Sepo Lina Mina. If I'm not wrong, that was the name actually. Lina Ma, I think that was the name. So this back propagation is the process through which you propagate the errors backward as a learning process, right? So here, what was the steps involved, guys? Can you just recall those steps as a feedback? Exactly. You process in the output end, then you send the feedback to backward. Okay, and that is how you move back and forth in the particular neural network, right? Is my understanding correct, everyone? Everybody, to let me know, please. That is how the back propagation works. Correct. So now, if I'm talking about the advancement that we had done recently in the 2000s, right? So in the particular part, do you know what was the first digital virtual chat box or maybe assistant? Everybody, think of it, and I believe most of the people are today nowadays using it. What was the first digital virtual assistant that we had? Google. Okay, fine, got an answer. In Word help document, Alexa. Okay, let me ask this very simple question to you all. How many people over here use Apples? Everyone. Can I have a plus one from everyone? Those who use Apple phones. Guys, actually, Siri was one of the first digital virtual assistant. Okay. It came in service in your iPhone 4S. If you remember, that was the very, very, very early versions of iPhone. Okay, like 10 or 1 decade back, right? So basically, Siri is one of the first digital virtual assistant that had that whole capability. Okay, at that particular time, it used to have two neural networks that used to give you this particular outputs and input, and used to take the inputs. Okay, now if you remember, guys, if I talk a bit more, okay, like just now scenario, okay, the current scenario, the 2020 era, okay, when we hit this year of 2020 and we started off with the year of AI, or the, you can say the era of AI. In November 2022, you remember what happened, everybody? Think of it. In November 2022, there was something happened that entirely changed this complete scope of generative AI. LLM, okay, Matthew is saying LLM, Chat GPT, very great. ChatGPT was launched. In November of 2022, this OpenAI organization they introduced ChatGPT, a generative AI combined with, okay, it's basically a model that is combined with large language models. ChatGPT and its variation actually achieved a new level. Okay, that was a completely crazy level of intelligence. Okay, these were smarter chatbots. They can perform research. They can support a reasonably good writing skills. They have realistic video generating, audio generating, image generating skills. Everybody. So the combination of generative AI with exactly after that Microsoft launched their Copilot, very good. So this guys, what I'm trying to say, this combination of this whole ongoing process of generating generative AI training with the large language model has resulted in the artificial intelligence ability to think and to reason. And this also might have the ability to imagine. Okay. So this whole thing, if I sum up in once, can I say guys, this ability of thinking, trying to imagine actually the scenario is what exactly is generative AI is. You are basically trying to generate using your thinking and using your reasons. Is my understanding correct, everybody? Right? Everyone perfectly understood this thing? Chalo. Now, let me ask you this one more question. Anyone who is feeling boring right now, because I want to talk about this particular part of history stuff because I want you all to be freshed up. Okay, because it's like 7 in the morning and you feel like aate aate we can't start the theory, right? So I want you all to be on the good page. Chalo. Everyone I believe is now ready to move ahead. Now, let me talk about this, guys. So this thing called as generative AI, what it does? So it does generation. Okay, it does generate something for us. Now you will ask, hey Dave, okay, fine, it's generating something, but nowadays, what are the other use cases of generative AI? So I believe it doesn't work only on the words, right? We're not generating only words anymore. We are also generating images, if I'm not wrong, guys, right? We can also generate text, right? Exactly. We can also generate videos. So how many of you have used DALL-E 3? Anyone who used DALL-E 3? DALL-E 3. That's a large language model. No? See everyone, this is DALL-E 3. Nope, but I want to know how exactly LM works, how to deploying the GPT and all. Okay, fine. Yeah, see, this is a DALL-E 3, guys. Okay, this is a large language model that is used to create images. Let's suppose, give me a prompt, guys. Anything. As mentioned over here, anything that comes to your mind. For example, a happy dog in the garden. So let's try that. A happy dog in the garden, right? And any specifics that you want to have, anything, it's paid, right? For now, I have got a free trial. You can also grab the same. It's free for right now, till like 10 or 12 credits, and then you can like buy credits for it. Okay. But for you all, like I have just got my subscription and all that. Sure. So guys, pug dog. Okay. It should be pug. Okay. It should be pug. Okay. So let's try. See, you have models. Okay. So if you want realistic, we'll have realistic. Let's create a 16:9 image. So it's generating now, everyone. Let's wait. 3, 2, 1. So if you come to this page, right? So it's saying waiting to start. Okay. And now it's generating. Okay. So now, just as we talked, guys, okay, try to imagine what would have been the back end process of it. Okay. Maybe we wrote a prompt, right? And this is the image. Everybody seems quite realistic, I would say. If you can notice out the background, it's quite realistic. Okay. The dog itself is a bit looking like a bit kind of you can say generated, a bit kind of like a animated one. But if anyone looks at the first edges, this is something that is actually real, right? We don't have to like go ahead and we don't have to like put anything, right? It would work like a search engine. Exactly, not like a search engine, yes, yeah. It's work like a generative engine. Okay, you're trying to generate something using your thinking. Perfect. How a same model is able to generate both text and images. For example, Gemini can generate both text and images. How? That's how they are trained here, Ganesh. And we are going to talk about one by one. Okay, that will come under the part when we'll talk about the GPTs, when we'll talk about the BART and all that. Okay. Search engine will not create a new image. Don't hear. these are the large language models that are specifically working with the image generation, but is stored data only executing, right? Shyam, see, let me talk about it, okay? I think now it's time we should start with a bit of theory. So, if you guys remember, there was a concept in your neural networks that was called as RNN, if you guys might remember it. How many of you remember this topic called as RNN? Let me answer all of the questions in once. So, guys, if I talk about RNN, so if I'm very very sure, RNN used to have a structure like this. Okay, if I'm not wrong, this is your input. Let's suppose, and from here we are getting an output. Okay, and in between you might have multiple layers. That's entirely upon you. So I'm just, for example, I'm just putting three. Now here we used to have something called as feedback loop. If I'm not wrong, is my understanding correct, everybody? Now, what kind of data we used to take in this recurrent neural network, everybody? Do let me know this, please. What kind of data we used to fit in this kind of model? Think of it. Just try to reverse time series. Okay, time series data. That's one use case. That's use case data. But what kind of data it used to be? Wasn't a sequential, if I'm not wrong. Yeah, exactly. Continuous. Very good. It was a sequential data, dear. Right? Now, think of it, guys, that how exactly this recurrent neural network used to work. It basically used to work on a sequence of data. Let's suppose if I've given a statement that, hey, my name is Dave. So what it used to do is that it used to take a user input from us, right? Here from here, we'll take a input. And now this layer started to work, correct? It started to work one by one. Like, let's suppose if this is the input and we have been given four words, right? Let's suppose anything that you can think of. Let me write, hey, I am Dave. Sorry. Maybe this is the statement that I want to go ahead with. Okay, we are trying to generate something using a recurrent neural network. Okay, now if we are having this thing, so obviously, firstly, hey will go inside, guys. Correct. This word is going to go inside. But right now, tell me, everyone, hey is a complete statement or hey is a part of a statement? Everybody, what is hey over here? It's a part of the statement, right? So that means this particular model is going to have two things, right? Here we'll have input that is going to be connected with some weights, right? And moreover, once these weights are processed, this will be summing up. Okay, I'm writing a plus over here. It will be summing up with a bias, right? And now this bias would have been connected to something called as activation function. If you guys think of it like back in your old good neural network days, right? And then this bias is also then connected to some weights. Sorry, this activation function is connected to some weights and bias, and then we are leading to the output. I believe that this is the traditional design of machine learning, deep learning model that you might have seen. You are connected with the input, you go with the weights bias, then there's an activation function that basically activates or charges that particular neuron, and then you get an output, correct? Now, what was the difference between a recurrent neural network and the basic neural network, everybody? What is the basic difference between them? Anybody think of it? I think it's very easy. Layers, neglect the layers for now. Very good. There used to be a feedback loop, guys. Okay, there used to be a feedback loop, right? And what this feedback loop used to do is, whatsoever input used to coming from over here, let's say that we are taking hey, right? Now hey, it was processed till this point of time. When it was activated, this feedback loop will pass the previous input and the output both over here. So basically, this data, okay, output was concatenated with the next input. Is my understanding correct, everybody? Am I exactly correct that this is how, like in layman terminology, how exactly RNN used to work? Chalo. If you guys are clear with it, can you please tell me what exactly was the problem with this particular network? What exactly went wrong? Exactly. Now this thing is, let's suppose here my context changes. Okay, my context is changing. Let's suppose I'm writing, "Hey, I am Dave," and let me add some few more statements over here. Maybe like, let's suppose I'm writing, "Hey, I'm Dave, and I'm working as a engineer." Okay. Moreover, I do like cookies. Right now, thing is, guys, if you notice it out over here, are we having two different context in sense that two different topics or maybe two different concepts to discuss? Okay, so are we having two different concepts over here? If you guys may think of it. So if I think of, actually I'm having more than two contexts. I see, I'm Dev, so this is one context. So according to ourselves, the language or the model that we are going to train should talk more about Dev, right? Then suddenly the context switches. Context changes to engineer. Okay, Dev is an engineer, right? So we are talking in the terms of Dev, but now the model should also remember engineer. Exactly. Now suddenly we're liking cookies. So now cookies is something that is new. Now here is the problem, everyone. Whenever you were using this recurrent neural network systems, what was happening was this feedback system, right? It has a very big problem. Okay. Do you know what is the problem is? Like as in the part of like long-term dependency, short-term dependency, I've seen that. Anything that you guys could be specific. Chalo, let me talk about it. Okay, because that is like our base use case that is going to be. So everyone, have you guys heard about gradient descent? Right? Everybody has heard about. What exactly would this gradient descent algorithm was? If I talk in the terms, so here somewhere I might have described this gradient descent because we were discussing about it in my earlier phase of classes. Yeah, this one. This is what exactly gradient descent is, guys. Everyone, if I'm not wrong, right? So what exactly is this algorithm doing? What the heck this algorithm is going to do? It's basically trying to give you the best parameters if you talk in this terms, right? You're trying to reduce the cost. At the same time, you're trying to get the best parameter, like the point where you can hit the error minimum. Is my understanding correct? The minimum point of error, right? Start with the initial value for the parameters, weights, and exactly step by step. Very good. So now if I come back to what we were discussing a bit while ago over here. Okay. Now over here, guys, there was an issue with this recurrent neural network part. Now let's suppose, let me give you a very great intuition, and I believe this will be kind of like a revision to what you guys have done already in the part of your recurrent neural networks, right? So let's talk in a bit. Okay. So talking in the terms of recurrent neural network, I'm going to make a very sweet and very small neural network. Let's suppose, okay, we're not going to make something very hefty that everyone is not able to understand, but we'll make something that everyone can understand and can easily get an idea of that. Okay, this is how what they wants to talk about. Okay, so let's suppose everyone that onto over here we have some particular inputs. Okay, so initially what I'm trying to think of is that, let's suppose if I'm talking in the terms of neural network, recurrent neural network to be very precise, everybody. So this was something that used to take the previous data, right? The previous few days or maybe the previous few data points to predict the next data point, right? So if we want to understand this, we need to understand how exactly RNN is working. Okay. So let's suppose everybody over here, I'm going to take an example that we have some particular thing. Okay. So can I say that input times weights, okay, plus bias. This is what is going to be our data that is going to get inside this activation function. Is my understanding correct, everybody? This is what is my first particular layer is doing, right? And this whole data is then going to be passed through something called as the activation function, right? Now, Generally, as per the general part of the neural networks, this particular thing would actually have resulted in output, right? As per general convention. Okay, this should have given us some output, right? But the thing is, guys, let me talk about a scenario. Let's suppose we are trying to predict the price of potato for tomorrow. Okay, and today's price is 18, and yesterday's price was 16. Anything that I'm taking off. Now, if I feed yesterday's values in it, okay, let's suppose this input is nothing but your yesterday's value, and we have done the calculation and we have got an output. So now tell me this, guys, if you have got an output, this output is for today or for tomorrow? Tell me, everybody. This output that we have just got over here, is it for today or is it for tomorrow? Tomorrow? Today? Okay. Guys, it's for today because our network doesn't knows what happened today, right? So that means we need to again train the model, but for today's data. Okay, that means here we need to have a loop that can go back, correct? And that can feed the today's data. That means if I talk in a hinge, so what can I say is a feedback loops makes both yesterday's and today's values to influence the prediction of what we are going to get for tomorrow. Is my understanding correct, everybody? Everyone on the same page or not? Please let me know. And then given a task, analyze sentiments which series the data for a given data point. Yes, that's what I'm talking about, right? So if you try to code it with the same thing with the example that we're talking about, that's exactly the same thing, right? So if we talk in this terms, guys, right? So let's say that if I'm talking in the terms of feedback, okay, so what exactly this feedback is doing? Can I say that we are basically trying to talk that today multiplied by, okay, today multiplied by the weights plus, okay, yesterday multiplied by weights. Is my understanding correct, everybody? You can say weight 2 and weight 1. That's entirely upon you if you want to differentiate. This is how exactly the feedback loop is working. But the thing is, if you look onto this diagram very precisely, there's a very like highly complicated graph to understand. Okay, this is something that a normal human being can't understand, right? So anyone who is feeling like they why we are discussing neural networks and this recurrent part and all that, just have a bit of patience. Okay, I'm just trying to make a kind of story so that you guys can also have a fresh up of your topics, and then you guys can directly move to the part of the first step to generative AI. Okay, because if you guys don't know, in case, so sorry, I think I've done something. Chalo. If in case if you guys are not aware about it, let me tell you, this recurrent neural network is basically the first stone or the first step to what you call as generative AI. Okay, then the second step is basically the LSTM that we are going to discuss. Okay, as of today. Okay, and this after that we'll learn the most advanced concepts that are like transformers. Okay, so this is how we are going to start, everyone. Okay, so if in a case if you guys are having doubts with this, you can let me know. So currently I believe some of you are aware about RNN, but you're not aware about the problem, about what exactly RNN used to have. For terminating that problem, we had LSTM. Now LSTM too have some problem. That's not like LSTM doesn't have some problem. So for terminating that problem, we had transformers. Okay, so that's how I'm going to go right now. Okay, sure. So let's talk about how is there any easy way to understand how exactly this recurrent neural network might work. So there is. So let's suppose, guys, if I'm talking, this is the data for yesterday. Okay, this data went to something called as weights. Any weights you can take. It's entirely upon you. And then it was added with some bias. Here we do have a function, your activation function. Any activation function you can take. For right now, I'm just considering it to be a sigmoid function. Okay. Now, according to our general information, this should have result in our particular prediction. Okay, basically the prediction for today. Okay, this is today's price. But are we interested in today's price, everybody? Are we anyhow interested in today's price? No, right? We are interested in what exactly is going to be tomorrow's price. So now what will happen from over here is this will give a feedback. Okay. To whom? To the next layer. So basically, guys, we ignore this part. Okay. We are basically going to ignore this whole part. This whole part will remain ignored for the current time. Okay. Now, if I talk about the next neural network, this will be basically the today's price. Okay. The same thing. Actually, you can just remember today's price is not actually, it is predicted price of today. Exactly. It's predicted price of today. So now what I'm doing is we are training a similar model, guys. Okay, we are training a similar model, but now if you notice, we do have feedback. So this is our today's price over here. Again, going to weights, going to bias. Okay, the activation function, right? And then we are having over here the predictions. Okay, I'm just trying to shorten it up as short as possible. So guys, haven't we actually calculated the predicted price for tomorrow by using a system of a recurrent neural network, everybody, like by taking the feedback from the previous system, right? This is like an overview, correct? Now let's try to impute some values to it and let's try to find out what exactly is the issue. Okay, because see, one problem over here is that the more this thing unrolls, okay, let's suppose that right now I'm talking about only 2 days data. Okay, that means using the yesterday's and today's data, we are going to predict tomorrow's data. Okay, now let me talk about this. If I give you 50 days data, is this data very big, everybody? If I tell you that dear all that you are having 50 days data or maybe 60 days data, and you need to predict like the prediction for tomorrow. So tell me, is this data very big, everybody? I think it's a very chintu mintu or chota data, hai, right? Correct? So yeah, everyone on the same page, right? How the sequential data can be interpreted for the data? I am dev and the engineer yesterday's and today's example. Okay, see, if you're talking in the terms of words tier, so firstly Dave will go, okay, and it will predict the next outcome. Now, basically, the thing is we're not interested in predicting this outcome anymore. We are interested in predicting what comes next after this. So this will be a series of inputs. Hey, I am, and then Dave. So basically over here we'll have 3 layers of input. Okay. Now see, let's suppose guys, if I keep unrolling this stuff to like 50 times. Now here is the issue. Now guys, the thing is one problem with this unrolling part. Okay, when we try to actually uncover this recurrent neural network is it becomes harder and harder to train by the time goes. Okay, because if you might notice, right now we are having two. Then let's suppose we are having 50 data points. Okay, 50 previous data points. So how many neural networks we are going to have, guys? Everybody. If we are right now having two neural networks that are training on just two particular data points, how many neural networks will have in the upcoming days? 50, right? So it's a computation. 50 neural networks to train. And guys, with each neural network, there's a feedback loop connected. That means, can I say that there would be a series of neural networks that will be connected by a feedback loop? Everybody do let me know this, please. Right? Sequentially, we'll have like dot 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 50 data points. Sorry, 50 neural networks, not data points. Perfect. Now, what's the issue over here? Everybody. Okay, let me talk about it. The issue is with the gradients. The time is one issue, and the second issue is gradients. Think of it like this, guys. Okay, let's suppose that if I take, okay, let's suppose if I'm having weights greater than 1 for now. Okay, let's take an example that with each particular layer going on, we have weights value more than 1. Okay, so now let's talk about it. This is input. Okay, and we are trying to break down our RNN into 50 different neural networks, right? Okay, can I have a confirmation is everyone is able to understand the example? Are you all able to understand this, guys? Anyone who is bouncing off till now? Yes, chalo, fine. Now, Let's suppose, guys, onto over here we are having 50. For me, it's difficult. Poonam, no need to worry. Okay, just try to imagine. Okay, no need to go in the mathematics. Just try to imagine right now. Okay, try to think of it. I have given you a chain of 50 data points. Okay, just 50 neural networks are there. Okay, just try to imagine, guys, you're holding a chain of 50 different neural networks. Okay, and they all are connected with a loop. Okay, just an arrow, simple as that. Now tell me, guys, with each feedback loop processing, we are basically multiplying some weights, correct? Right? It's like a very basic neural network that I'm trying to frame. That was the first time when this was processed. So input times the weights, right? Everybody. So let me change the color actually. That will be more better. Yeah, inputs times the weights. Now again, think of it in this way, guys. Okay, you have changed your train. That means there will be again a multiplication of weight. Perfect, everyone. Again, we change the train. Again, there will be multiplication of weight, right? Think of it like just we are changing the loops by loop by loop by loop by loop, right? Again, W4 dot 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 dot. Till what we will go, guys? Till what times the weights will keep on multiplying? W50. Sure. Now W50. Now everybody do let me know this, okay? This weights is something that we decide by using gradients, right? Now let's think of it that the input or the weights that we have taken is, let's suppose, 2. How many times we are going to have 2, guys, then? Everybody, if the weights remain constantly each and every neural network that we are going on, how many times we are going to have weights? Raised to the power 50. Very good. Can I write like this? Double multiplication 50. Now tell me, guys, this weight, this value is going to be a very enormous value, right? And now, if you think of it in this scenario, right, don't you think, guys, our particular neural network, instead of having a optimal state, instead of having a state where it can move freely and can reach the optimal parameter, don't you think it will keep on bouncing? Because the steps that we are going to take are quite big, that they're big enough to, like, we'll just see. Let's suppose that if it is this gradient descent is right, what exactly is the main agenda behind gradient descent? That we take steps so that once we are reaching this optimal state, our steps are slow. Okay, they're very small so that we can reach the optimal state very, very easily, right? But let's suppose if the steps that you're going to take are big enough, don't you think we'll just be bouncing off, guys, like this? Tell me, everybody. See, this is a gradient actually. Okay, check it out, everyone. I'm trying to make you guys visualize for this. If you're taking a very big step, don't you think you'll be just bouncing off here and there in the entire gradient loop? Check it out. If this is your parabolic curve, right? And let's suppose a step we are taking, it's very big, so we'll just be bouncing off here, 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 correct? Are we reaching our optimal state? No, right? Each step is 2 to the power 50. Yes, Akhil. We are just for an assumption, we can say, yeah, it is 2 to 50. Okay. We're not reaching this particular state. So, guys, this is the problem with a recurrent neural network. This problem is called as exploding gradient problem. Exploding gradient problem, everybody. This is the problem that we have with recurrent neural network. Anyone who's aware about this? I think some of the people might be aware about this exploding gradient problem, if I'm not wrong. Anyone who's aware that what exactly is this issue? Bouncing, we know. No, I'm specifically talking about this exploding gradient problem, dear. No? Chalo. If that is step size big. Okay. So basically, guys, what will happen over here is this gradient will explode over here. Okay. Because it is not able to find the optimal state, so it will keep on bouncing. It will just keep on your neural network to iterate. Each word is iterated as single input, which can cause issue. Exactly, Akhil. And since we are not having the optimal step size, okay, we are not having an optimal number, so we won't be able to go ahead and we won't be able to predict, right? Predict the perfect thing. Now you might think of, okay, Dave, let's suppose we're not taking something very big. Let's take something small. Maybe your thinking might be like, okay, Dave, right now you have taken weights like 2, right? Why don't we try something with a smaller one, 0.5? I think that would work. Is my understanding correct, everyone? Opposite is always correct, right? Shall we give it a try, everybody? Exactly. Very good, Prasanna. Now, let's talk about this, guys, okay? Previously, we had input that was 2 to the power 50. Now, if I take, this will be input multiplied by, okay, 0.5 to the power 50. Now, what's the issue, guys, over here? Again, the same issue. If you notice, just a vice versa. Sakshi, we are taking anything, okay? Just a random data. There's not nothing as specific I have taken. It's just a very small value, okay? So now the issue is, guys, if you now check out the gradient, instead of bouncing off, it will not be able to complete the iteration even. See, the steps will be so small that you won't be able to reach the optimal state. You will have finished, your particular iteration will be finished till you reach the optimal state. Exactly. Okay. 1 divided by 2 to the power 50. Very good. Okay. That will not reach you. Very nice. Very precise. It's time consuming, and we will be actually consuming all the particular iterations before reaching the optimal state. Okay. So this is the issue over here. Let's try to conclude this thing. So when a gradient will have a huge number, we'll end up having a greater step. Okay. And instead of getting an optimal parameter, we'll jump a lot, like we have seen over here. So then we thought of to, okay, let's take something as a smaller one. So when we took the smaller step, so instead of getting the optimal parameter over here, we are just getting out of the step. We are just getting out of the epochs. We don't have enough number of iteration. And even if we have enough number of iteration, the steps are so small that model is not able to get to the optimal parameter state. And this problem over here is known as vanishing gradient. Perfect. So I believe firstly, does everyone have a clear picture of what exactly a vanishing gradient is and what exactly exploding gradient is? Okay. And guys, if you don't know this, this is one of the most asked interview question whenever they are talking in the terms of neural networks. Okay. Specifically when we are dealing with the sequential data, this is the one of the most asked question, that what is the exploding gradient problem and what is the vanishing gradient problem. Why it is called exploding? Because basically neurons are particularly a particle, right? So they, whenever they're bouncing, they're basically exploding. And here it is called vanishing because after a time your gradients vanish. Okay, they are not no more in the picture, right? So that is why the name is vanishing gradient, and that is why the name is exploding gradient. Is this thing perfectly clear to everybody? Do let me know this, please. Everyone. Perfectly clear? Chalo. Now, after this issue, we needed some solution on it. Okay, there was need of some solution that can actually think of in such a way that it shouldn't go very much far, that it shouldn't go so do we need to take a optimal need of weight? We need to take a optimal weights there, but the thing is, don't you think it's a very time consuming process, specifically when you're dealing with a data that is sequential and that has to be fed along with a long proportion of time? Let's suppose even if I'm talking about 50 only, so you have to basically pass 50 data elements one after another, and that's only one statement. Okay, let's talk about Gemini a bit. Okay, let me show you a real time use case. So let's suppose over here, so over here, let me see. Okay, see, so this is a cosine matrix. Okay, if you guys are not aware about it, let me remove it and let me talk a bit about something easy. Okay, yes, chalo, this one. Supply chain. Okay, so I have written this whole statement. Okay, this whole statement over here. Okay, and I wanted to rephrase in the form for tone formal. So guys, tell me, if I give this particular statement to my neural networks. Okay, specifically this recurrent neural network stuff. How many words we are going to have? Everybody. Because if you notice, just read this out once. Can you see that how many times the context is changing? Everybody. Firstly, we were talking about the supply chain management, right? And then we were talking about this global economy stuff, right? And then we were talking about reducing cost, improving customer satisfaction, streamlining their operations, and all that stuff. So, see how frequently this context changes. Context means, guys, the agenda, okay? The topic, right? It will have large data. Obviously, it is going to have large language, LLM. But right now, I'm talking as an example, Samarth, okay? So, if I'm talking in the terms of example, if I feed this data to different neural networks, don't you think it will obviously is going to have either one of the problem? Either it will have the excluding gradient problem, or either it is going to have your vanishing gradient problem. Because this word limit, exactly, it will not react properly. It will explode. Okay. Because either it will start learning a very like it will start learning very fast, so that it will just keep on bouncing, or it will learn very, very, very slow rate and it will vanish. Poof. Right? So I believe this thing is okay. I think my screen share is stopped. Let me reshare it. Just asking, as it is an English language RNN, will it be trained on the basis of grammar? Generally, dear, it trains upon whatever you have feed it. Okay. If you talk in the terms of grammar, it might not be very, very, very precise, I would say. Okay, it might not be very precise, Samarth. I think I don't know how exactly this screen share stopped. Chal. Okay. Okay, fine. Chal. Till this point of time, anybody having any issues with understanding this whole scenario? Anyone who is not able to understand? Can I have confirmation from each and every people who is present in the meeting? Good to go. Okay, everyone enjoying, right? There's no one who is not able to understand. Okay, I don't want that. Okay, yeah, Dev, kya kar rahe ho? Right? Potato price is okay. Changing context is same. Okay, can we have a break right now? Okay, let me have the confirmation from other people also. Guys, do you want a break, everybody, or should we continue? You guys can let me know. Accordingly, no, let's continue. Okay, what about the what's about to take? Okay, Ubaid is saying break. Can I have everyone over here continue break? Oh, quite a polarizing opinion. You guys are forming up 5 minutes break. Okay, yeah, we can take that. Okay. Okay, let's take two breaks in between. 5 minutes, 5 minutes. What do you say, everybody? Okay, if in case it will be lot, we can take 5 minutes, 5 minutes. Okay. So right now it's 7:58. I expect everyone to be back by like 8:03. Okay. And meanwhile, those who are having questions, they can let me know. Okay, I'll be happy to answer them. Yeah, Poonam. Poonam, can I share you the access to microphone, please? I think that will be very great if you can directly ask me what exactly are the issues. Okay. You do have the access, dear. Please ask me what exactly are the issues that you're facing.
Hello, am I audible, sir?
Yes, ma'am, you're audible.
Okay. I'm not understanding this difference input W1 and then input
Okay.
to what?
See, let me talk in the very, very general terms. So, are you aware about the neural network structure? Like how exactly a neural network is, Miss Poonam?
Yes, yeah. I
Okay.
don't remember, but we learned it
Okay,
in
sure, no
computer
issues.
science class.
So let me show you. So I have a visualizer, guys, that can help you to understand. Okay. So this is what exactly is going to be a neural network, right? I believe so. Let me remove it.
Yeah,
Let me come to one layer only, right? And let me reduce this also, and maybe we can reduce this also. Okay. So this is like you're having only one input. Okay. There are two neurons, and there's an output connected to it. Okay. Now this was exactly the same thing that we are talking about. So instead of having an input singly, now I'm having an input like in the text format. Now thing is, Miss Poonam, whenever recurrent neural network works, it works in this way that one layer has a feedback, okay, that is yet connected to similar layer. over here. Okay, and that layer is connected to another layer. Because see, if I'm talking in the terms of a statement called as hey, this is Dave, right? So this is one input, right? And generally, a normal interpreter can process this whole step but won't be able to understand the whole context. So in order to understand the whole context, we need to break down the statements. Okay, we need to break down the words one by one. So in the first go, he will be passed. Second go, there will be passed. Third go, they will be passed. So this is how the recurrent neural network works. Okay, and when the working happens, there is the issue with gradients because we need to take very peculiar steps, very optical steps. I mean accurate steps. If the steps are not accurate, either your gradient will just vanish, that will it will go invisible or intraceable. You can say you won't be able to trace it, or it will be so big that you will be just keep on bouncing up here and there. Okay, you won't reach the local minima. That's the issue that we have discussed about. Okay, and about the concern of this weights and bias. So weights and bias are associated with a part of a neuron. Okay, initially you can take any random values and then you can like tune them one by one. Okay, you can let me know, ma'am, if you are now comfortable like with this all things.
Yes, sir. Yeah.
Okay, dear. Thank you. Okay, seems like there was some few questions in the chat box. I did think seems like, and guys, yeah. By the way, guys, this is a website that is called playground.tensorflow.org. This is like a official playground from TensorFlow. So if you guys want to explore it, you guys can explore. So this is where like you can explore how exactly neural network is working. So here you have your epochs. What is the feature here in the diagram? I use the API key from the playground. Yeah, I'll share it. So basically over here you have a lot of stuff to yet you can do. So this is like a kind of circular data. Okay, this is your output. And if you want discrete output, you can go like this. So this is exactly how the color of neurons and all the things are. If you want to see the test data, this is your test data, this is your tree data, everybody. Okay. And even if you want, here is like a brief introduction to what this neural network is and how exactly this whole thing responds. Okay. So if in case if you want to add up some inputs, so here you are having inputs over here. Okay. And then here we are having some neurons, like your hidden layers basically. So if you want, you can increase your hidden layers like till 8. Okay. And then here is your output. Okay. So features times the weight. You can see each and everything has weights. Okay. So if you want, you can like edit the weights according to your choice, everybody. Okay. And then you can start it. Like let's suppose you can set the epochs. Okay. Over here. Let's suppose I'm setting to 20 epochs. See, now you guys can visualize this neural network, everyone. Check it out. Can you see, guys, everybody? And you might see over here also the losses that are going on. Here, check it out, guys. Okay. So if in case if you guys have not explored it, so this is how exactly, and this is right now running at epochs at 1000. Okay. And then I can stop it, I can reset. And if you want, you can also tune up the learning rates over here. Suppose I'm setting it to a 0.03. Let's take it to ReLU, your rectified linear. If you want regularization, you can do that. For now, I'm not doing it. Now, if you run it, check it out, everybody. This is how the ReLU is working over here. Okay, see how exactly one neuron, okay, is working. See, check it out. You can like visualize it, guys. Okay, you can just mention out like how exactly you might see the out change in the output also. Check it out, everyone. Okay, so this is a place like you can like, go ahead and you can like visualize each and everything. And this is the data set that is we are working on. So if you in case you want to learn about it, you can just check it from over here. We have to pay for the zero payment. Zero payment needed, Samarth. It's a free platform. Okay. I actually got it in research. Like I was doing some research and I found this very website where like you can visualize each and everything. It's in the school actually. You guys can visualize. Okay, try to this experiment with this. Chalo. Are you ready to begin, guys? Everyone, now refreshed. There's something that you can play off with now, right? Chalo. Now let's talk again back in the terms, right? Now, due to this very issue, okay, due to this issue of this vanishing and exploding gradients, the issue was with the recurrent neural network was it was not able to remember a lot of things. Okay, like let's suppose if I have given a very big statement and the context is changing in between, so recurrent neural network was not able to remember a lot of things, right? It used to forget. Previously, we had a concept that the neural networks don't remember anything as such, okay? Because if you might have learned in your CNN in your NN classes, so there was a concept that the neural networks don't learn. Then came the concept of RNN that okay, the neural networks can learn. Then we had a problem that this neural network has short-term memory, right? It is very have a very short memory and can remember very less things, right? And as human nature is greedy, हम लोग लालची होते हैं, so we formed something new. And that something new resulted in forming up something called as LSTM, long short term memory, everybody. So this to resolve these issues, we got into something called as LSTM, everyone. Long short term memory, everybody. This is what is the name given to this particular algorithm, everyone. Okay. So now I'm going to share one of my PPT. I don't like to teach with the PPT part, but this is something very helpful for you all. So let me share it really quick with you. So let me see in my repository where it is. I searched, it is coming LSTMRD. So basically, dear, GRU is kind of like a implementation, more you can say a more enriched implementation of LSTM. Okay, not enriched, I'll say both work same. The way it is implemented is a bit different. That's it. Okay, both the things works really same. There's no any basic difference between them. But there's a kind of you can say what you can say like it's the working principle is different. Okay, you need access. Oh, I think I have made it on a different account. So no worries. I will talk about it. I have requested access. We'll see. Now let's talk a bit about the LSTM part. Okay, what exactly this LSTM is, how exactly this thing works. Okay, and what exactly are the things. So in RNN, we use this feedback. Okay, to like to use the same data. Okay, to unroll the layers and do that all stuff. But there we had this problem: gradient, vanishing, exploding. Now to avoid this vanishing and gradient problem, okay, this LSTM came into play. Now, guys, if you're thinking of, firstly, I would like to take an idea from you all. What are you thinking of this LSTM? Is it something that can actually, like you can say, simplify the process of learning a sequential series? Everybody, are you guys in that mindset? Everyone, do let me know this, please. Maybe everyone, I think, would be on the same page. Yeah, Dev, I think if this is a solution, this might be something simplified, right? So let me break down that particular hypothesis. So if you compare this RNN with this LSTM, so LSTM is a very complex and a complicated structure. Okay, it's way too complex than what you guys have seen in the normal RNN structure. Okay, so let me show you an image of LSTM. So this is LSTM structure basically. I do have researched a lot on the LSTM part in like few years, and this is the stuff. So let me show you. I'm just thinking of a better image. Yeah, this one. This is a very good image. See guys, this is a LSTM. Everyone. There's a brief structure to LSTM. We'll be discussing about the structure and this architecture and all of this thing. So now if you notice it out, it's not like this is just one part. Okay. Here also in the A we are implementing LSTM. Here also we are implementing LSTM. Okay. So basically if I talk in the very hinge, so this from here the input is coming into this one, and we do have different gates that we are going to talk about. Okay. And then we do have this output that will be passed on towards the next LSTM layer. Now you might be thinking of Dave, why we are then using it? Like, can you tell me about the use case or maybe something that can be helpful? So let's start discussing about it. Okay. Firstly, before going with LSTM, what is H? H is the input over here. This is H1 is input. Okay. This HT is output here. Okay. to filter relevant information, I guess. Yes, dear. Basically, whatsoever will give us the input over here in the xt1. Okay, so this xt1. First, for now, let's remove this terminology. These are like very dreaded terminologies over here. So we can talk in the very easy terms. Here's the input. Okay, just need to simplify it, guys. Okay, you guys are actually aware about this all of things. I know. Okay, just the thing is that you need to just simplify it out. So here we will talk in terms of output from the layer one. So input from the layer one resulted in output. Okay, and this output was then passed towards this one. Okay, where if you notice it out, guys, can you see there is a new input that is going on? Everyone, can you notice out this is a new input, right? We have given an input over here. So if I write now, okay, let's suppose if I write x, so either isn't this today's price, everybody? Can I say like that? Isn't this today's price? Tell me, everybody. So what will be yesterday's price, guys? Everybody. If today's price is x, what is the yesterday's price? Can I say x t minus 1, time minus 1, 1 day before, right? And then if I'm trying to predict the tomorrow's price, what is going to be? Tomorrow's price is xt plus 1. Very good. So isn't the same thing mentioned over here? xt minus 1, xt and xt plus 1. Is my understanding correct, everybody? And now, if I'm talking, so let's suppose if I feeded this data, feeded a data to this xt minus 1, okay, this xt minus 1 hasn't feed it to a neural network. So this output that we have got, can we say this is the output for t minus 1? Everybody, correct? And then can we see the same thing for this one also? That from here we'll give the input and we'll get output. So this is the txt input, sorry, the output for xt, right? So the same thing isn't it written over here, ht minus 1, then ht. These are the output that we are getting. Is my understanding perfectly clear, guys? Everybody? No need to worry, I'll talk in the very depth about each and everything. We're going to talk about right now. Okay, now let's start. Okay, chalo. If you guys are clear with this terminology, I want a clarification on all of you all. Why do we need ht minus 1? Taking the example, dear Prasanna, we have actual value. Yeah, we are just taking the examples. Okay, xt minus 1 is representing the actual value of yesterday. Okay, we are feeding this actual value of yesterday in the neural network so that we can predict the today's price. But we don't need it, right? We don't need today's price. We need to calculate the price for tomorrow. So this information is passed down towards the next neural network, where the next data that is of today is feeded and is added. If you guys might notice, see here we are adding both of the data together to form up a new output. Okay, I'm going to talk about the structure. Let's wait for a while. Okay, so before going ahead, guys, I want a confirmation from you all. Are you all aware about the sigmoid and the TANH activation function, everybody? Is everyone aware about this both? Because these are going to be our building blocks basically. Okay, if you guys want, you can tell me, I can recap for you all. Do you guys want me to recap or maybe give you an overview of the same? Everybody, are you guys on the same page? Sure, let me tell you that. So, if I'm talking in the terms of, yeah, sigmoid activation function, so I believe everyone remembers this S, a very famous S, right? So basically, guys, this S basically tells you, let me put it in a different way. Okay, this S is, I think, something you might have seen in the logistic regression also. So whichever input you give on X, okay, on the x-axis, here's your x-axis. It tries to predict the same on the y-axis between 0 and 1. That is what is a sigmoid activation function is doing. So if you all remember the formula, it's very easy actually. So if I say f of x, okay, that means the function of x, the formula goes like e to the power x divided by e to the power x plus 1, if I'm not wrong, right? The same formula that you might remember in your logistic regression classes. Remember, guys? 1 by 1 plus e to the power minus x, right? So now let's try to initialize this. here E is basically Euler's constant, everyone. Okay, Euler's constant, if you might remember, this is a fixed constant, everybody. That is, what's the value? I think it's 2 point something, if I'm not wrong. Okay, we'll just search it. Euler's constant value. Okay, it's like 2 point something, if I'm not wrong. Yeah, see, 2.7 exactly. So 2.7. That's the value of Euler's constant. So now let's try to put something into this. Okay, so if I say that on my x we are having a value 10. Okay, predict the value on y using sigmoid function. What will the value, guys? Okay, firstly, what will the formula, everybody? E to the power 10 divided by e to the power 10 plus 1. Is my understanding correct, everybody? Perfect, eh? And if you just do a bit of mathematical calculation, so e to the power 10 is basically 2.7 to the power 10. So can I have an idea about how much it would be? Think of it, guys. It will be nearly around 20,000, 20,589, if I'm not wrong. Just calculate it once, and anyone, how much it is gonna be. I think it is gonna be near around 20,589. Uh, Point is also there, right? Point we are the 2.7. Okay, so it is going to be 1 over here, if I'm not wrong. Can anybody just pull up the calculator and can do this? You can just let me know. 0.99. Very good. So and here we'll add 1, so it will be 0.590.1. Okay, and if I do a quick coordination, so it will be 0.99, and I can just put a bar over here because it will continue. So this is the result of a sigmoid activation function, everybody. So basically what we are doing is we are trying to put a value on the x onto the y between 0 to 1 using this sigmoid function. That's the first thing. Okay, second activation function that I'm going to talk about is your tan h. Okay, difference is in tan h, everybody, we are having the values, okay, in between -1 to 1. That's the difference. Okay, so if you take any value on x, okay, you take any particular value on x, it will result in a converted value to -1 and 1 in your y-axis. So let me give you an example over here also. So let's take 5 over here. I think I have not given the formula. So formula for this goes like, uh, if I'm not wrong, my e to the power x minus e to the power minus x divided by e to the power x plus e to the power x. Now tell me, guys, if I have taken f of x equals to 5, okay, here the value of f of x is 5. So what is going to be my output over here? Everybody, tell me. Take your time, no need to worry about. I'm just trying to recap your concepts. Okay. Onish, you have raised your hand here. Do you want to ask something, dear? Oh, no, I'm good. Okay, fine, dear. E to the power 5. I think e to the power minus 5. E to the power 5. Sorry, it's 5, dear. It's not 3. It's 5. Plus e to the power minus 5. What is this value, everybody? Can you please tell me? I think it will come close to like -1. Everybody, you can just check it off once. I think it will be coming near around -1. Correct. I think it is -1 if I'm not wrong. Just you guys can just confirm it once, yeah, and then we'll move. Okay, to move forward. Okay. So this is the two combinations that we are going to use. Okay, the sigmoid function and the tan h function. Okay, everybody. In the LSTM part, we'll be using these two sigmoid functions. Okay. So I want you all to have a clarity on the same. Okay. If you guys are not clear with it, sir, what is the use case to TANH? Okay. As I told you there that the TANH function is basically used whenever you want to put a value into a scale of -1 to 1. Need is that, let's suppose, let me give you a scenario to explain. Just give me, just let me drink water, guys. Okay, thank you for waiting. Chalo. So going with the question, everybody. So basically, guys, the sigmoid function, okay, it will act as a gatekeeper. Okay, see, let's suppose that the sigmoid function basically acts very good whenever you want to get your output that lies perfectly in 0 and 1. Okay, it's basically very, very, very perfect to make any binary decision within the LST. Okay, so a value that is close to 0 will signify that, okay, we don't have to remember it. And the value that is close to 1 will signify that we have to remember it. Okay, that is how exactly this particular sigmoid function will work. Okay, whereas this TANH will limit our non-negative inputs. Okay, now this particular tan value, okay, that we are talking about, this will represent the memory in our particular LSTM. We're going to talk about what exactly these all things are, how exactly this remembrance and non-remembrance is working. But this is like the use case of 10H and the sigmoid in our part of LSTM. Okay, the very basic use case. Now, before beginning, I would like to talk about what exactly is the basic functioning of LSTM. Okay, so there's a blog, guys, that I generally prefer a lot whenever I'm talking in the terms of LSTM, because also I have read some this like before, like very long time ago. Okay, so there's a blog actually. I'll tell you to refer that. Obviously, that's a very good blog and will help you to understand a lot of concepts. Okay, so firstly, we need to remember something. Use case of TANH, please. As I told you, dear, that this where this basically, if I talk about a sigmoid, so sigmoid is just limited to this 0 and 1 part. Okay, whereas your TANH is using this -1 functionality. So this characteristic is crucial because the cell state that we have not talked about till yet, Sushmita. So to maintain the cell state is basically the memory that LSTM uses. Okay, that's why I'm not talked about it yet. I'll be talking about. That's why I told you. For a TANH use case, we'll have to just wait a bit there. Okay, because to make you understand TANH, first you guys need to clear with what exactly cell state is. Okay. So the cell state represents the network's memory basically. If I talk in a very hinge, so the cell state terminology, it represents the network's memory and its values. Okay, its value needs to be able to increase and decrease based upon a new information at how much we need to remember and how much we don't need to remember. So basically, TANH allows us this flexibility to adjust this limitation of knowing this information. Okay, that is what exactly this TANH use cases in the LSTM part. So if you want to remember, sigmoid function is like a gatekeeper which will tell you that okay, this information we have to remember, this information we don't have to remember, and TANH is basically telling you that okay, how much we should remember this information. Like, what is the percentage of remembrance? Correct. That is what is the use case to TANH is there. Okay. So if I talk in the very gist, so sigmoid and TANH guys works together in LSTM. So sigmoid works as a filter controlling which information should flow through the LSTM, and TANH regulates that value in the cell state. Okay, so that your particular cells, your LSTM cells can remember. Okay, this information I have to remember to till what percentage. Okay, so if you combine these two together, everybody, so your LSTM can excel any particular task that requires long-term memory and can also have the ability to selectively remember or forget the information over the extended sequences. Is this clear to all? The particular part of sigmoid and the TANH, everyone? Are you all clear with the use case, everybody? TANH works like giving priority. Behur, you can say like that, not like exactly like priority. You can say like it tells you that how much information you need to remember, right? It's given signal in which given point they need to work upon. Exactly, dear. dear. Okay, Samarth. So it basically is going to work combinedly together. Everybody. Okay, fine. Chalo, are we good to move ahead, everybody? Is everyone on the same page? Everyone able to understand, visualize it properly? Okay. And there's one more thing, guys. Okay. See, whenever you guys are learning neural networks, okay, that's what I have experienced in my whole time. Whenever you guys are trying to learn any kind of neural network or any kind of activity that is related to machine learning, AI, DNN, generative AI, the one major thing that you need to understand is you need to imagine the scenario. Okay, like let's suppose if I'm talking right now, it's not like I'm just talking over here. It's like I'm trying to make you guys, I'm trying, okay, I'm just, that's what I'm saying, I'm trying to make you guys imagine this whole scenario, that this is how that world of neural networks might work. So if you guys can imagine, it will be really really easy for you to learn how exactly this NN framework and all the things works, everybody. So this is just a small request and again like a suggestion for you all, that try to just visualize everything. Okay, just try to think of a neural network, maybe like a just think of it like you are having a cube, and that cube is having some pipes that are associated with something. Okay, and then again that pipe is flowing off through the network. That is how basically I imagine this scenario. Okay, chalo. Now what I'm going to talk about is few terminologies that will start talking as of today one by one. So here are the list of the terminologies that we are going to talk, everybody. Uh, yeah. So over here, the very first terminology that we are going to talk about will be your input gate. Before that, even I'll be talking in the terms of memory state or memory cell. Please share the notes and the PPT at the end of the class. Yeah, I'm not sure you'll have this. Dear, I think this one is quite amazing to be very honest. Okay, let me see what we can do for it. Okay, I'll do something. Okay, no need to worry. I'll do something for it also. Check. So this the first thing is memory cell, that we'll be talking about what exactly is memory cell and all that part. Then we are going to talk about forget gate. Okay. Then we are going to talk about input gate, and then we are going to talk about output gate. Okay. So I'm basically referring to the same diagram that is written over here. So we have a forget gate, we have an input gate, and we have an output gate. Okay. So now let's start talking, everyone. Okay, let's start talking about how exactly these all things are going to work. Okay. So everyone, the very first thing that we need to remember, or maybe not remember, basically we need to understand over here is in LSTM, we don't have any structure that you might see in the RNN, everybody. Okay, we don't have a structure like this going with a feedback loop every time. Okay, we don't have this structure. Instead, what we are having is a very generalized loop. Okay, have a check. I think I have made it too big. Let me just minimize this stuff. Yeah, that will be fine. Okay. So now let's have a look, everybody. So let's suppose this is our previous state input. Okay, this is our previous state output, PSO. Okay, now over here there is this X. Okay, what is this X? This X is nothing, is called as a point wise operation. Okay, point wise operation, everybody. Maybe you might be thinking of we were talking about LSTM, how from where this point wise operations comes into play. Let me tell you. So guys, if you remember, RNN basically works with the part of data that is sequential, right? And along with that, the main expression or the main thing that we are targeting over here is the context, that how exactly the model is behaving when the context changes. So let's suppose from the output we got a matrix. Okay, everybody, we got a matrix. Let's suppose this matrix is 2 3 4 1 0. Okay, this is the metrics that we have got. Okay, and now what we're trying to do is over here, guys, we are trying to do a pointwise multiplication with the part of the current input that we are going to get. Okay, now let's suppose this is also a metric. So if you guys are aware of word vec, how many of you are aware about word vec over here? Everybody, can you please tell me, everyone? How many of you are aware about word vec, word to vec? Okay, no issues. If you're not aware, no issues. Uh, let's suppose I'm writing two words over here, king and queen. Are these two words, everybody, do let me know, are these two words similar in the way of context? Not in the way of words, guys, in the terms of context. Okay, in the terms of what you can say is agenda, right? I think they are very much similar. I think 99% similar. Both of these words states royalty. Both of these words states a kind of higher position of honor. But if I say king to poor, what is the similarity? Is there any similarity between these things? King to poor? Yeah, exactly. Contrast. No, there's no contrast between king and poor, right? So basically, dear, the thing is, let's suppose here this is the output, and I'm also having a matrix over here. Let's suppose 1, 1, 0, 2, and again 0. Now, what exactly pointwise operation is? You need to just multiply it like this. That's it. That's what pointwise operation is. Matrix multiplication, actually. That will be easier word. So what is the output from over here, guys? Everybody do let me know this, please. What is going to be the output for the matrix? I think it is going to be 2, 3, 0, 2, 0, right? Now here is the interesting part, everybody. The points that you see as 0, guys, we don't have to remember that. Okay, that's how exactly LSTM works. The point that you are seeing that is 0 is that we are going to forget this. We are not going to remember anymore. Okay, we are going to forget this. And the point that are having marked, that is what we are going to remember, everybody. Okay, so this is the first part of what exactly is the pointwise operation is. Perfectly clear to everybody? Anyone who is not able to understand this part? These are like prerequisites that I'm giving you. Okay, these all are like prerequisites, everybody. So 0 is for forgetting, 1 is for remembering. What about 2? No, dear. Then we will be passing this data to the sigmoid function, right? So let's suppose, dear, if we have passed this function, forgetting means data loss. No, dear. Akhil. No, no, no. Not forgetting. Remember the context changing, Akhil? Right? The context changed, right? So if the context has changed, do we remember? Do we need to remember each and every piece of data? No, right? We need to remember just the important information, correct? That is relevant for us, correct? So that means that if, okay, if in the case, if we are having some amount of information that we don't need to remember for the upcoming time, we'll forget that and we'll keep those particular information remembering that is needed for us. Okay, now let's talk about where this thing will come into play. Okay, but two is changing information. Well, two is remembering and the changing of information. Okay, we are trying to remember and change the information. We are adding up the information. Okay, we're not changing it completely, dear person. Okay, I'm going to talk about it. Okay, no need to worry about. X will always be a matrix. Yes, yeah, okay. X will be a matrix because I believe, dear, anything that you work in machine learning or in the artificial, that's a matrix, right? Everything is matrix, correct? Sure. Let me give you an idea about it now. Okay, I want you all to have a focus over here, guys, so that I can clarify one thing that is very, very, very important over here. Okay, and the input will also get converted to matrix. Yes, okay, exactly. Okay, sure. I want you all to have a view of this, guys, because this is something that I think is very relevant for you to understand. Whenever I'm talking in the terms of neural networks, or basically specifically in terms of LSTM, the very first thing is the previous state output. Okay, from over here, whatsoever comes, okay, goes to the very, very, very first thing. Okay, goes to this very first thing called as forget gate, and before that, there is something that is called as long-term memory. So there's a straight line, okay, in LSTM structure, and this is called as long-term memory over here. This line is basically representing a long-term memory, everybody. And over here, I'm just putting some particular values for them. You don't need to be concerned about right now. We'll be talking about it. Okay, X, and I'm here. We can put something. Okay, I'll put in the upcoming time. Okay, now the bottom part of the LSTM works a bit different. Check it out, everybody. So here we are going to have the input that we are going to pass. Okay. So now, guys, if you might think of here, we are having actually two things. Okay. From here, the input is also coming. Okay, everybody. And from here, our data is also coming. So what will happen to this both? Anyone? Can you please tell me? If this input is also coming, if this input from our end is also coming, what will happen? This is input from the outer layer, this one basically, and this is the input from our side. What will happen over here, guys? At this particular point, exactly, both will get concatenated. Okay, both will perform concatenation, everybody. Both will get added. And now this added data, everybody, will be passed on to the weights and the bias that are corresponding and will be passed towards the sigmoid function that is present over here. Okay, and this sigmoid function will eventually return us a value. Okay, now the value that will be returned to us will be the percentage of the long-term memory that we have to remember. Simple as that. So this first gate is the forget gate, everybody. Okay, this tells us that how much information we have to forget, how much information we have to keep. Okay, sigmoid function will return only with 0 and 1. Like for the metrics there, eventually, like if there is some particular value over here, let's suppose, Prasanna, if we are having 1, okay, if we are taking this for example, if I'm taking 1 over here, and then if we are going to have an input that is also 1, right, concatenating it, and let's suppose we are having some weights over here. Okay, I'm not talking strictly in the mathematics term, dear Prasanna. I think that's why we might be having this question. But if you will talk in the strictly in the mathematical terms, then the results will be different. I'm just trying to plot a picture over here. Okay. So that is the first part of what exactly is LSTM is, guys. The first part of it is called as the forget gate. Okay, this is the forget gate. How do we classify that which needs to be forgotten? This will give you idea here. We don't need to get an idea. Okay. This particular gate will give us an idea which part we need to forget and which part we need to remember based upon the data. So as I said before, this will return as a matrix. Okay, that will give us an idea that okay, this is the data that we don't need to remember, and this is the data that we need to keep in mind for the long term. Okay, Prasanna, Lakshmi is saying, can you please repeat again the first part? Okay, Lakshmi, you can let me know, dear, that which part, this part or this part? The forget gate part. Okay, dear. See, if I'm talking in the terms of forget gate, the very initial thing is the input will come. Okay, if you want, I can just let me make a better and a fresh diagram for you all so that you guys can easily remember that capabilities. Okay, so over here, see, this is a forget gate. Okay, so from over here, your input will come in, that is your ht1, ht minus 1, as you guys might have seen earlier over here. Okay, ht minus 1. Okay, check it out. This ht minus 1 is now going to be combined with your new input. Suppose, let's say xt. Okay, now this both the things are going to get combined together. Okay, and this data will go inside your sigmoid function. Perfect, right? And the sigmoid function will now go ahead and will now give you a cell state. As our input, yes, this is our input from yesterday, if you remember, right? I think we talked here somewhere about yesterday and today, if I'm not wrong. Somewhere I think we talked about ht minus 1 is our yesterday and today, something like that, if I am not wrong, right? Now the sigmoid function is going to give me a value x, and this is called as cell state. The cell state has the only job, okay? The cell state is the only thing that we need to have, because this is something that will tell us how much data we have to remember, okay? How much information we have to remember, okay? So context change example, let's suppose if two words are similar, everybody, okay? Let's see in this example, okay? This is the forget get, and let's take out an example for the same. If you're having king, okay, as I think you guys have confirmed, and if you're having queen, everybody. So these two words are very, very, very much similar in the context, right? Let's suppose I have written king is very generous, okay? Queen is kind. Now guys tell me, if this both the words are very similar, and even if the context is changing, do we need to forget something, everybody? If these two words are very much similar to each other, okay, I'll repeat my statement once again. If these two words are very, very much similar to each other, do we need to forget anything over here? No, right? Correct? Hai? So, and due to change in the context, right? Let's suppose instead of this, if I say king is very generous, poor are getting less paid, right? So now guys tell me, if now these two statements are over here, do we need to forget a part of information or not, everybody? Let me know this, please. Right? Because obviously there's a very strange change in the context, right? There's a complete change in the context. So if I give you the formula for straight for this particular part of forget gate, the formula goes like very simple, okay? No need to worry about. This formula is actually very, very, very simple. So can I say, everyone, just think of it. Can I say the weights, okay, combined with the previous state output, okay, plus new input multiplied by the current weight? Is my understanding correct, everybody? Which one to forget, sir, king or poor? Obviously, Prasanna, if we are having this king as the first statement, so we'll forget the part of king dear, right? Okay, poor will be remembered because the next statement is going to talk about poor, right? Bias. No, dear, Hemant, I'm just right now plotting some basic equation. I'm not giving the exact equation right now. It's just a basic equation to give you an overview. Okay. So firstly, do let me know, guys, if you guys are clear with this very basic understanding of forget gate, everybody. What exactly is the forget gate? What if the third statement is king? Very good question, but actually I was going to come to that statement. Now, guys, think of it that first statement is on king, second statement is on poor. Let's suppose that if there is a third statement and we don't know, right? We don't know that if it is going to be a part of like a king or a poor, right? So, guys, what will happen at this moment? That is what this particular state is for. This is what exactly this point was meant to, because LSTM doesn't works on that operation. It will completely forget something. It will keep some of the information in the memory, guys. That is what exactly LSTM is. Long short term memory. Exactly, memory cell. Very good. That is what is the methodology it works. Okay. This particular thing will remember some part of the king, and using that it will create the next statement, everyone. Is this perfectly clear to all or not? Please do let me know. If the third statement is neither poor or nor poor, maybe it's the third something. Prasanna, in that case, context will again change, right? If the third statement, guys, is not talking in the terms of king nor the poor, then in that case the context will again switch, right or not? Please let me know. Then again we'll have to do the again point wise matrix calculation. Again we'll have a new matrix at which information we have to remember, which information we have to forget, right? And there will be some amount of information that we will store, and there will be some amount of information that we forget based upon third context switch. Perfect. Everyone able to understand this information? For each context there will be some information to be remembered. Exactly. If context is changing, again need to start from beginning. No, dear Sushmita, that was the issue that we were having in the terms of R&D, right? Correct. We won't be going ahead. We won't be starting. We'll keep on moving ahead in this one. Okay. How data to be converted in the metrics format? I just told you over here. And we are going to talk about how exactly. So let's suppose if I'm talking in the terms of strings, everybody, or maybe the words. So words are getting converted by a technique called as word to vectors. Okay, this is a technique that will help you convert the words into vectors. Okay, this is a technique actually. Okay, generally for right now, since we are learning, so we'll be using proper matrices. But once you guys will be comfortable, I'll start using this synonyms like word to vec and all that. Okay. For now, I don't want to burden you up with this lot technical jargons. Okay. Chalo. So I think this could be. Can we reach to a closure today with this, guys? Everybody, because tomorrow I think we have a lot of works to do. We have to discuss the entire architecture of how exactly LSTM works. So what do you say? Should we continue or should we end it over here for today, everyone? It's too much for today. There we have not started even Poonam for today. Okay. It's just like I have just given you the overview of how exactly LSTM was. Okay, how exactly each and everything works. Chalo, no issues, everybody. And about the part of notes, guys, I need to figure it out, like how exactly I have to put it, because I think we have done a lot of cartoonist over here and there. We have done a lot of artistic things, so I'll have to think of it like how exactly we have to put it. Okay, no need to worry about. Okay, you can share tomorrow. Yeah, sure. Kishore is saying how many classes? Kishore, I'm not very like I don't have accurate information on the same. You can talk with the same with the IntelliBot team there. They will let you know like what exactly are the how many classes we are going to have. Okay. I know it is for this week. Okay. What about the schedule that you have given? That's for this week, dear. Okay, Prasanna. That's what how I'll be planning my sessions to go with today. Okay. Just this was the first class I think on your generative AI, if I'm not wrong, guys. Correct? Everyone? Right. So how was it? How was the experience, everybody? Good? Nice topic. Easy to imagine. Correct? Sure. So tomorrow, good but complicated. Yeah, I think, dear, it will be a bit complicated as we move forward, okay? Because it's something that is advanced, everyone, okay? So I'll be very blunt with you all. Now, it's not something that you guys are going to have in your machine learning or deep learning, okay? It's not something. It's something that is advanced. It's something that you guys are using, okay? I planning to learn AGI where I can start. I think Shriram, I can't answer this question on this particular session. Okay, this is something that I'll also have to explore, like which are the best resources. Sir, have you really implemented generative AI in your workspace? We are currently working on it, Prasanna. Okay, we are currently working on it. It's in progress, basically. I'd say. Okay, because there's a hell lot of things that we are working on right now, and that's one of it. Do you have LinkedIn, Bhagirath? I do have a LinkedIn, but I'm very, very, very socially inactive. Okay, I do have like one or two followers, I think. Okay, that's it. It's like I have created that one like 5 years or maybe some years back, and I don't use it. Okay, sure. So, okay, guys, with this, today's session comes to an end. Thank you for joining. It was really nice talking to you all. Tomorrow, I will suggest you all to be prepared mentally and with copy and pen also, because tomorrow we are going to have a lot of discussion, guys. I'll be very blunt with you at the very first moment, because tomorrow I'm going to tell you about the architecture of how exactly LSTM is going to work. So be prepared, everybody. Okay. Chalo. Thank you all. Have a great day. See you all tomorrow. You're supposed to share the PDF. Yeah, dear. So, Sanju, I'll share it tomorrow, dear, because there's a lot of cartoonistic that we have done. So I'll just put it in one PDF and I'll share with you tomorrow. Okay. Chalo. Thank you, everybody. Have a great day. Enjoy.